All right, folks, hello. Welcome to MATHurdays. Math's so fun. We do it on Saturdays. My name's Teresa Wells. I've been hosting this MATHurdays thing for over a year now, where we meet every Saturday and we look at a math block that we start off with a little community building. We go into a math routine. We dive into a juicy, rich task and have a discussion about it. And then we finish off with a little community building. And so let's go ahead and jump in and get started today. If you don't yet have, well, all of you have the link to the slide because, you're in here. Welcome. And I'll just continue to post it in the chat in case you close it for any reason. We are going to do almost all of our work in the Google Slides and just occasionally use Zoom for the chat box and to turn on your microphone. If you come on down to slide 4 and 5, I'd love to hear a little bit about what's going on with you all. Go ahead and share your successes and celebrations. This can be in teaching, this can be in math, in your personal world and more. And I'll add mine here. My celebration is I escaped my home in Virginia because there are a bajillion of those little cicadas coming out. I've been in Florida now for almost 2 weeks, and it is warm and sunny and quite lovely. And so when those guys go back, I will come on back. So that's mine. And let's see if we've got some other fun things in here. Oh, who won the free workshop last Saturday? Okay. No worries, Elisa. So the Zoom is a little different than the platform we traditionally use. The microphone, you usually have to kind of minimize your web browser and then you see your microphone in the Zoom feature. If you ever get it on, feel free to say hi. Oh, there you go.
I just found it. Yeah, it was exciting when I came home and saw, oh, we wouldn't have our MATHurdays. I was already doing a 10 o'clock session with Pamela Weber Harris, and she let everyone enter a drawing, and I was the one lucky winner. It was so exciting. So I will be doing proportional reasoning for free this summer.
That is so cool. And what a great experience too. Who is spending a long weekend in Canada and getting outdoors? How's the weather up there? And what part of Canada?
Hi, Teresa. It's Kathy from Edmonton. I don't know what it is in Fahrenheit, but we're above 0. So above 32. We've planted, but then it freezes. So all our plants are in the garage and around the house. And so I'm hoping we can put things out permanently and pull out our bicycles and things because we just put that away for the winter time. There's no way that I'm going to ride my bike in the snow.
Yeah. So, it's something interesting in our elementary and even middle school. We do a lot of conversions between customary units and metric or Fahrenheit and Celsius. And what an advantage to having to do that now that we are, able to do classes virtually from places on the other side of the continent or the world where this stuff really starts to matter. So thanks for joining us. Laura, are SOLs all done?
Good morning. Buenos dias, everybody. They are, thank goodness, because I don't think I could have done it anymore. I think I'm here in Virginia and our SOLs is the state test. And, just with everything we've been through, it just felt, me personally, it felt really unfair to make these kids take the test. But, we did the best we could. The kids did amazing. It just was really exhausting, and we're just glad it's all over.
Yeah. Well, I know that takes a lot on a regular school year, but this year is definitely special. So hope you are earning yourself some relaxing time now that those are finished up. And other people getting grades in. Looks like they're getting ready for the summer. Awesome. All right, folks, so let's just jump right on in. We've got a nice small group with us today, and happy that you all are here. We're going to start on slide 6 with a favorite routine of which one doesn't belong. If you would like more resources for this routine, slide 5 has links that go to it, and you can get the templates that I have set up along with many other which one doesn't belong is already created, so less work for you as the teacher. So if you would, grab a doesn't belong symbol from slide 6 and move it to the quadrant that you think doesn't belong. Once you have one rule, try to think of a different rule. Why would a different quadrant maybe not belong? And there are plenty of those symbols to come up with as many rules as you can and continue to add them to those quadrants. And of course, this template can lead us into some discussion, but I find the next slide, I like to do these two together because of the affordances. Come on down to slide 7, double click one of those little boxes. They're actually just a ton of text boxes on the same slide. And tell me, why doesn't this belong? If you selected multiple, go ahead and click on multiple. And I'm going to call in a couple folks to share out. If you have a green highlight around yours, just a heads up that I'm going to call on you. And let's start off with the one in the upper right. Somebody said this is harder to do. Could you elaborate a little bit on that?
Sure thing, Teresa. It's Kathy. I looked at the others and I felt the one in the top left for sure was folding in half and half and half. And I assumed the ones at the bottom kind of took that same approach. But the third, you can't simply just take the edge of your paper and fold it over and meet in a symmetrical kind of way. You would have to kind of double fold it and then judge so that it lines so that your thirds or your columns, in this case, I think, would all match in the same size.
Ah, cool. Yeah, that thirds, anyone, especially who's taught elementary school and trying to teach fractions knows that thirds can be difficult to do on paper for sure. How about the person who chose the bottom right, who said, maybe this is tissue? Tell us a little bit more about your thinking.
When I looked at it, it looks so thick and wadded. It just looks like a different type of paper. And the other three all look like regular copy paper. And this just looks like a different type. And maybe it's been folded so much, you see all the thicknesses where you fold over and it just gets almost wadded up like a tissue.
Ah, very cool. And then we have one in the bottom left that says it's a fan instead of a box. What do you mean by a box?
Hi, this is Stephanie. So I guess I said like a box, like a rectangle. And I just thought of it as boxes instead of rectangles. So the third one was folded like a fan instead of like the little rectangles.
Neat. So it almost had a different rule for folding. Somebody else mentions that, and I love the teacher language here. So I'm going to ask you, what does it mean to fold things like hot dogs or hamburgers?
Hot dogs would be more lengthwise, whereas hamburgers, the hot dogs are going to be longer and more narrow, whereas the hamburgers are going to be wider and taller along the side. I can't describe it correctly, but I've heard that used a lot, especially with younger kids.
Absolutely. And so in mathematics, we develop vocabulary, we develop terms to help clarify meaning. And this is one that I was really hoping was going to come up, folding things like hot dogs or hamburgers. So if you can imagine a regular sheet of paper, and you can fold it one way and it looks more taller than if you fold it the other way and it looks more like a square. So that's the idea of a hot dog bun or hamburger bun. And we can use that to understand folds and explain them over a microphone. And this is going to actually lead us into our activity today. We're going to do a paper folding activity. And I thought that we'd start off with the which one doesn't belong, because you all have already identified several things that we can mathematize in our task. I'm going to move us down to slide 9 as we jump into our task. This is the reasons why I even bother with rich tasks. These are the 8 NCTM math teaching practices, and you're going to see all 8 today. And before we begin, I'm going to give everyone the opportunity to take the problem solving oath that's on slide 10. I'm going to say it out loud. You can say it with me and type your name in the chat box if you're going to pledge this today. I, Teresa, promise to try my best. I will make sense of patterns and numbers. I will use manipulatives and drawings. I will make mistakes. I will ask questions. I will listen to other ideas. I will stay engaged by always trying to find another solution or representation. I am a problem solver. I make the world a better place. If you would like to take that pledge, go ahead and put your name in the chat box there. It's always exciting to see young students or veteran teachers take this pledge. And I do have a little video here that I would love to show so we can have some context in what it means to do some paper folding. So I'm going to go ahead and turn this on. If for some reason you can't hear it or it's not playing for you, you also have the ability to watch it on slide 11, but I'm also going to play it for the recording. And this is the paper folding challenge.
Back over at NASA, our team is finding out that folding a football field-sized piece of paper isn't exactly a breeze.
For instance, the fact that it turns into a giant windsock with the littlest bit of a breeze. There's air trapped underneath it.
But they managed to rein in the billowing parachute without any tears for an official Fold 1.
Let it fall. Pull the slack. Oh, that was beautiful.
They reposition for the next crease.
We're gonna fold that direction.
It's like trying to fold the world's biggest bed sheet.
It's crumpling in weird ways. It's not folding smoothly.
But the team manages to smooth out the wrinkles and make folds 2, 3,
Hey, notice we're all getting a little closer?
4, 5,
Everybody to this side for 6.
and 6. Neat and tidy tuckings.
It's actually like an airbag. Lift.
However, with each pass, the additional layers make it harder to heave over. And at Fold 7, everyone and everything is starting to puff.
A lot of air. Yeah, and it's not going down. There it is. Yeah, push your foot.
7 is squashed out. Now, the team is about to go for 8. If they achieve this, they will bust the 7 paper fold myth.
See how everybody's very quiet? Because we're all anticipating busting this myth. We folded it 7 times. We're about to go for number 8.
Looking good. I think we're gonna do it.
The paper tries to dig in its heels, but is losing its grip.
Come on!
And we did it!
Yeah! 8! 8!
It sure feels satisfying to beat a paper myth to a pulp.
If you draw a line all the way down, you'll be able to intersect every layer, and that is a true 8 folds. And that busts this myth.
There's no stopping our out-of-control paper pushers now. If it's worth doing, it's worth overdoing. Carrie trucks in a giant rolling pin to flatten this piece of puff pastry some more.
Flat as a pancake!
As smooth as rolled dough, it folds back easy as pie.
9.
9!
To achieve double digits, the paper is too heavy for the team to lift themselves, so they stick a fork in it.
Drive in. Drive in.
Whoa!
That is a definite 10.
Topping 10 is going to be tough. Thanks to their buddy Exponential Growth, the paper is now 1,024 layers thick. It takes every ounce of strength they have to bend it.
You got it?
That feels like an honest 11 to me.
Nice!
Not only did they bust 7 folds, they turned it up all the way to 11.
Definitely put this one to bed.
Absolutely.
Well, as far as our definition for the myth goes as the fold, we've got it long, we've got it flat. If we do any bit more, it's just going to be a semicircle. We got 11 folds out of a football-sized piece of paper. We busted a myth, and we're going to go home before the sun completely goes down. 11 folds.
I didn't think it was possible.
Should we go to the NASA gift shop?
Woo!
Yeah.
All right, folks. So that is our challenge for today. The myth is that you cannot fold a sheet of paper more than 7 times. You've gotten some context with the earlier pieces from the which one doesn't belong. And typically when I've done this problem, I will do one of 2 ways. I either give them very specific directions, like you must fold it like a hamburger each time, but I'm going to leave this open to you all because you are going to collect data in any way you like. On side 12, for example, is group 1's work. There are some pieces of data that you're required to gather, such as the number of folds and the number of rectangular segments. But you'll notice there are 3 other columns. There's lots of information that you could choose to collect about this. So as a team, you'll decide what it is you want to collect. You can fold different types of things, tissue paper, regular paper, Post-it notes, and more. So let your imagination run wild and think about what other pieces of data you could collect and what generalizations you can make. The objective for today is to notice patterns that you see and to make generalizations about them. So at this point, I'm going to go ahead and pop you into your breakout rooms. And those have started. You can head on into that breakout room. And if you can still hear me, you've got people in the breakout room waiting for you. Just be sure to minimize your web browser and you'll see Zoom hanging out in the background there. And then you can click that little message that says, hey, go into your breakout room. if you're watching this recording, I've given them 60 seconds to come on back to the main room. During this last 20 minutes, I have been in and out of the breakout rooms, listening in to what they're doing. In one case, I gave a suggestion, which you'll see in group one. They kind of were finished, so I gave them a suggestion of figuring out how many intersections are there. Group two was already talking about something very unique, the cuts. And group three was focusing on the parts that you don't see. And so we're going to investigate those things in just a minute when everybody returns.
We need at least 2 more hours of paper folding before we can go on to the conclusions.
Oh, that's what I love about this is it's a great kind of project-based learning because the kids will find their own thoughts and like their own patterns, and it's so cool. All right, folks, welcome back to the main room. I hope you enjoyed this activity, but even more, I hope that you are not done with this activity. I hope you want to keep playing with this activity, keep investigating what other patterns you could find. That's one of the joys that I find in math like this. And one of the things that I love about this task is that, if you're teaching exponents in this exponential growth, it's a great task to really see it. But I also like this because of how accessible it is for multiple grade levels. I have a second and a third grader, like children, and they were playing around with this task and noticing and wondering so many great things. And we could do this with high school as well. But I'd like to showcase 3 very unique ways of looking at this problem that aren't the obvious exponent way. And the first one I'd love to look at is on slide 15. So you can follow with me in Zoom, or you can follow with me on the slides. But particularly this group, I mentioned that I would have them come back and talk about the parts they don't see a fold in. Group 3, would you talk us through your investigation and what you noticed about your numbers on slide 15?
I'm not exactly sure what you want me to say, actually. So are you asking me for the pattern?
Yeah, why don't you start off by just explaining what you noticed here with the 2 8s and the 6 8s, and just define like what you mean by the 2 and the 6 and the 8. And then you can bring us down to the one where you did 27s.
Okay. So when I'm teaching grade 3, a lot of the kids have a hard time understanding that the part that's not shaded is not the bottom part of the fraction. So I liked folding this paper and finding that the part that I can see on the outside of my 2 papers, so the top and the bottom, was 2 out of the 8 that I had. And the part that was inside the fold was 6 out of the 8 that I couldn't see. And so then Gail and I folded our paper into thirds as many times as we could. And then we talked about what that would look like for fractions also to see the pattern. And so there was 27 parts and 2 were on the outside. And the pattern that we could see was, again, the parts that we can't see was 25 out of 27.
Wonderful explanation. I'd like to invite everybody else in the chat box there. Do you notice a generalization about the numbers that were just stated there? So we had said 2 8s and 6 8s, 2 27s and 25 27s. If you see any kind of generalization, go ahead and type that in the chat box so we can make some connections. Stacy, you bring up an important part about denominators and addition. Specifically, do we add those denominators? Can you tell us a little bit about how you saw addition in this explanation?
Well, when she showed it and you have that one piece of paper and you have to add it all up. I still have college students that will tell me that you add straight across both numerator and denominator. And this is like, it's a great visual for them to realize, oh, no, we have one. And so the only thing that we add together when we add those common denominators is those numerators. So a really cool way to look at it.
Yes, indeed. And Kathy also mentioned this idea of the pieces, but you mentioned it in the part whole. How do you see the parts in the whole here? What makes this unique?
If I see I'm just looking at the one with the yellow there, the 27s, that you see one part is 2, the parts that you see, and then the parts that are inside are the 25 parts, and then the whole thing was 27. So, and you're thinking in 27ths. And so you have two, like, I'm not explaining myself all that well, I don't think, but you have one part that you see another part that you don't see, and all together it makes the 27 parts, or as we count in 27ths.
Yes. So the idea that you see some and you don't see some. And I love the connection to probability that Lisa brings up. Why is it so important that kids are understanding that there's a part you see and you don't see in terms of probability?
I just know that on our state test and I've never done this before the last couple of years, but on our state test that pops up occasionally. And we're asked, what is the probability that you don't get such and such in a probability of an experiment? And I think it's important for kids to realize it either can happen or it doesn't happen. So sort of the opposite idea of what you want to happen versus what's not going to happen. And maybe
you could also segue this to odds.
Yes.
Yeah, so now we have the probability, the theoretical, or the odds. Remy also brings up the importance of when we see all 3 numbers, the part you see, the part you don't see, and the total number of parts, that's how we build more conceptual understanding. And often in mathematics curriculum, we just focus on like one of the numbers. So here we really see both. Very cool. The next neat thing to look at, if we can come to slide 13, and this group, I love that I was able to give you just a little prompt here without even talking, and you just went with it in such a cool way. Join me on slide 13 and tell us about intersections and what patterns you're starting to recognize here.
I'll start first. Mine is on the bottom right, and I had a piece of patty paper that I could fold 8 times, and I ended up with 64 sections, which they're numbered, and or they were actually squares because it was square patty paper. And then I circled the intersection where 2 segments intersected. So there were 64 squares, but there were 49 intersections of 2 segments. So it's 8 folds squared gave me my number of sections, but 7 folds, or then less 1, 7 squared gave me the number of intersections I had with two segments coming together. I hope that makes sense. And I don't have mine marked, but they're like Laura's. And so Laura's is sort of the same thing. If she had a piece of paper that she could have folded 8 times, and she only took a quarter section of it.
That is neat. I love the way you generalize here. You said 7 squared intersections. Can anyone see other things squared, 8 squared, 6 squared, 5 squared, 4 squared, 3 squared, 2 squared? Does anyone else see any of these things squared in the examples on slide 13? If so, just turn on your mic and tell us what you notice.
6, 7, 8, 9. Teresa, I'm almost thinking maybe there's 9 squared edges, but I'm not sure. Possibly. I mean, I'm looking at Laura's picture, and I went along the left-hand side and I counted down. I said, okay, there's 1, 2, 3, 4, 5, 6, 7, 8 edges. No. And then then I would go, okay, then I said, but there's 9 vertical lines going down. So there's 9 sets of 8. And then I would do the same thing across. I'm just thinking I need to like touch and count. So let me count on my little picture and see what happens.
And while you're doing that, can I just confirm that you're talking about even, I'm going to put a little circle on it, even the points of your paper, is that right?
I was really looking at the edges. So like each square has, or each rectangle has 4 edges, but some of those are shared. So now I want to count and see, I'm just going to take a little piece and see what happens with edges on just a small piece. And then I'll come back.
Cool. All right, you keep working on that one. What about those intersections? I've highlighted some yellow circles in there. Does anyone see a connection with those yellow pieces?
I'm just thinking 4 squared and 3 squared. I don't know.
Tell us where you see 4 squared and where you see 3 squared.
Well, if I'm only looking at the dark, the 4 by 4, which is 16, and then the intersections are 3 by 3. So that's kind of what I put in the chat. My guess was n squared and then n minus 1 squared. But I'm not sure.
And I wonder if that continues for any amount, which is a great way. You know, we can look at the piece with 32 and count those intersections. This is the part where I like to leave enough foundation for kids to go, huh, but not really fully explain it, not really fully bring that out. Is there anybody else who saw what Kathy just mentioned there and can just rephrase that for us just to make sure our understanding is clear?
I think I understand. So we've got the 3 squared in the middle, and then if you add squares all the way around, you make the 4 squared, and then you'll increase to 5 squared, 6 squared as you get bigger and bigger. So it's a very visual representation of exponents or the squaring.
Absolutely. Oh, very cool. And I see some things in the chat box here. Gail mentions that this can continue down to 2 folds, 4 sections, and 1 intersection.
But 3 doesn't work. But
what
3, but when you do 3 folds or 8 or 5 folds, you don't get the squares. If you do an odd number of folds, it doesn't work out the same. But if you do an even number of folds, it does. I'm playing.
Yeah. And so then we start folding papers in different ways to figure out, why does it work for odd numbers? Why does it work for even numbers? And which ones build squares and which one builds rectangles? So there's some really cool math in that one also. We're having some great discussions. I did want to bring up on slide 14, this idea of a cut. And Kathy, Rini, and Stacy were talking about this, and I snagged a little picture so you could see some cuts. But what's really neat is, would you all tell us, what did you discover when you made this little tiny slit in your paper?
If you fold it and then you cut it on that fold, that cut, no matter how many times you fold it, every time you fold, if you cut halfway through that fold, your cuts will always be on the inside of the paper. And it actually creates some pretty cool symmetry if you hold it up to the light.
Which is a fabulous extension too. So in that image on slide 14, one important thing to notice is that when Kathy cut this, she just kind of nipped at it. there is just this tiny little cut here, just a tiny little bit. And it's not cutting all the way through. It's just a little nip. And so when Kathy opens that up, if you hold it up to the light, it almost looks like little twinkle stars kind of coming in. So my question to you all, and even your students, is, are there the same number of cuts as there are intersections? Now, it's probably one of those things where you start to get a hypothesis, but you just don't know without doing. All right, so I wanted to bring your attention next down to slide 20. These are some things that I thought that you might have chosen: the number of folds, the total number of sections, the total number of intersections, area, in other words, fractions, the length of the sides. Gail was even coming up with what I was calling the perimeter, or the number of like folds if you were to cover it up with toothpicks, because two sides will often share a fold. And these are all great things that when kids start to do the task, they'll notice that there are patterns in the numbers. And those patterns bring up reasons for, hey, why are we doubling it? Or why are we tripling it? Or why are we halving it? And bring some purpose into the patterns that we develop. I'd love to leave us with a video. And then Gail, at the end here, if after the video, if you did have something else, definitely feel free to share. The video is on slide 19, and it shows some of the really cool mathematics that comes out of this. So I'm going to make sure that I share my sound. Great. Let me stop and reshare. I'm still a Zoom learner. Stacy, yes, I'm going to continue Math-Through-Days in the summer because we have a lot of teachers who might be teaching virtually, and I'm expecting a new wave. So here we go.
Hello, I'm Brittany Gallivan. Have you ever heard the commonly accepted belief that no one can fold a piece of paper or anything in half more than 8 times? That was 6 folds for this piece of paper. Back in 2001, my honors pre-calculus instructor challenged anyone in the class to fold anything in half 12 times. This is a sheet of gold foil, 4 inches by 4 inches, 11 millionths of an inch thin. It is actually thinner than the wavelength of visible light. I folded the 4 by 4 inch gold foil in half 12 times. My teacher stated that he had misspoken and that the challenge was actually to fold any piece of paper in half 12 times. The paper folding challenge is often used as an example of exponential growth. If you fold paper in half 50 times, you could reach the sun. Every time you fold the paper, these double. What people weren't taking into account for was the radius section. In an initial fold, the radius section is minimal. As the folds get larger, this radius section takes up more and more paper. Although this doubles, the amount of paper that you need in the radius section for each fold actually squares. As your number of folds increases, you need 4 times the length to achieve the next fold. Where's my pen? Oh. I derived 2 limiting equations for folding anything in half. One was for single direction folding. When solving for length, pi times the thickness over 6 multiplied by 2 to the n plus 4 times 2 to the n minus 1. And then the
All right, folks, I am going to leave you with that. She does bring up a couple more equations that she figured out from this, and has the Guinness World Record for the number of folds. And I love where that video stopped because you can really see that curve and that she talks about in the video. So folks, that's the top of our hour. I hope you enjoyed today's lesson. Most importantly, I hope that we end today with you thinking about this paper folding, and the next time you're talking to someone, whether they are a second grader or just someone in your social community, and you're thinking about paper folding, that you challenge them and then you ask them what patterns they see. Because when we start to see those patterns in our real world, we make connections to tables, and that brings us into algebra and calculus and more. It's been a pleasure. If you have questions, I will hang on, but otherwise, happy Days, everyone.
Thank you again.
And thanks, Lisa. Yes, I will be presenting with the Global Math Department on June 1st, talking about teaching in online and face-to-face settings at the same time. Sometimes it's called concurrent or simultaneous learning.
I think you probably should post that next week so anybody who's never attended one will have an idea of where to sign up.
Awesome. Thank you.
Enjoy the rest of your vacation.
Thanks.